The application of Newton's method to logistic regression results in an algorithm called iterative reweighted least squares. We're considering logistic regression, and we just computed the gradient and the Hessian of minus this L function, which was minus the log likelihood function for logistic regression. So way back up here, we were doing binary logistic regression. This was our model, and to compute an MLE, we wrote down the likelihood function, and then we took minus the log to make things a little bit easier, and then we took the gradient, we got the gradient, and we got the Hessian, and they were these two very nice linear algebra expressions. And now we would like to apply Newton's method to this problem. And Newton's method needs both of these ingredients. So let's see what happens. So we're going to apply Newton's method, and Newton's method, we'll apply it to this vector w. It says to iterate to get wt plus 1, you take wt and subtract minus the inverse of the Hessian times the gradient. And the Hessian here, so just a brief aside, let me say that you can always remember this formula by analogy with the one-dimensional case. Because in the one-dimensional case of Newton's method applied to the optimization problem, it's xt plus 1 equals xt. This is for some, just generic, x single dimensional quantity, minus the derivative of the function, whatever the function that we're trying to optimize is, at xt, divided by the second derivative at xt. This is Newton's method for optimization. We're applying it to the derivative of f. We're applying Newton's method to the derivative of f. And here, this is the same thing. It's, t plus 1 equals t minus, and the only sort of natural way to divide, the only natural thing for the second derivative of a multi-dimensional function is the Hessian. And the only way to sort of naturally divide by a matrix is you take the inverse. And the only way to combine a matrix with a vector is in this way. So this is easy to remember if you can remember the one-dimensional form of Newton's method, 1D Newton. And this is ND, or I guess actually D dimensional, because N is in RD, or W is in RD. So let's see what happens now. So this is the formula that we want to, and let me put it over here. H was this Hessian matrix of L, and that was A transpose B A. That was this thing right here, where B was, this diagonal matrix, and A was our design matrix up here with our data. And the gradient G was, what was that? That was A transpose times alpha minus Y, where alpha was, maybe I don't think I wrote it here, but I meant this alpha to be the sequence of alphas, alpha 1 up to alpha n. That was this alpha, actually transpose. So alpha transpose times alpha, A transpose times alpha minus y, the vector of y's, the vector of target values. So let's plug those in here and see what happens. So this equals Wt minus A transpose BA. Let's suppose it's invertible for now. We were just supposing that all that we know is necessarily that it's positive semi-definite, but let's just assume for Newton's method to apply, we need it to be invertible. So let's just cross our fingers and hope for the best. Hopefully it'll be invertible. So this is this inverse times the gradient, which is A transpose alpha minus y. And so this is, we could stop right here. This is it. We have a nice expression for we can evaluate all the quantities in this Hessian and this gradient easily. And so we can compute this. I mean, assuming that this is invertible and all. So we could stop right here, and this would give us our Newton, the application of Newton's method to get the solution, and we would just iterate on this. But I'd like to rewrite this in a little bit different way, to put it, because it can be put in the form of the solution to a weighted least squares problem. So let's rewrite this. Let's factor out of the first part the inverse and A transpose, and let's also factor out a B from this. So in order for all this to cancel, we're going to need A here times W transpose, and then when we multiply that, that's going to be good. That will cancel. Minus, now we need to put a B inverse to get rid of the B, and then we'll have alpha minus y, I think. Let's see. So the B goes away, and yes, and then we're left with this original thing times alpha minus y. So we can rewrite it in this way. And then let's define this quantity here. This is a vector. Let's define this to be z. A transpose B z, maybe zt, where zt is just this thing. I'm just rewriting things here in a different way. So this is a nice expression here, because this is wt plus 1. This is a very nice linear algebra expression because it has an interpretation as the solution to a weighted least squares problem. You might recognize this as looking sort of like the solution to the least squares problem. That was when we were doing linear regression. We found that the solution to the linear regression problem was, with the design matrix, it was A transpose A inverse times A transpose Y. And that was our WMLE. But it's different in this case. It's now we have this B inside here. And this B matrix, this was that diagonal matrix with the alpha quantities. And this B matrix is a weighting matrix. It's essentially a weighting matrix, and we refer to it in that way because this is the solution. I keep saying it's the solution to. What is it the solution to? Let me write down what it is the solution to. It is the solution to the following problem. So this is the solution to the weighted least squares problem. And that is the following. It's the argmin over w's of the sum, as I goes from 1 to n, of bi, I'll say what bi is in a second, zi, the z's are given, minus w transpose xi squared. Sorry, that looks like a little funny. Let me just make to emphasize, it's just the dot product here. So if we didn't have these b's, oh, and this is where b, the B matrix is a diagonal matrix with entries b1 to bn. So these b's are just alpha times, so bi is alpha I times 1 minus alpha I. I just put b to sort of simplify it because in general this is referred to as a weighted least squares problem, and these b's are the weights. So when we were doing linear regression, we were essentially solving, when we did the MLE for linear regression, we were solving a least squares problem, and we didn't have these BI's hanging out here. We didn't have these weights. It was a yi here also instead of z, but that's not particularly important for this discussion. But it was minimizing something that looked like this, but without the BI's. That was just a regular least squares thing. And now with the BI's, it's called a weighted least squares problem. So these are the weights. Weights. BI. So it's just nice that, you know, you can sort of the result of this applying Newton's method to this problem actually gives you something which is essentially a weighted, it's a solution to a weighted least squares problem. And so as a result of that, people refer to this as iterative reweighted least squares. And it's, why is it reweighted? Well, the iteration is clear, you're iterating. And the reweighting is because at each step, you get different BI's, because remember the BI's, that depends on these alpha i's, and the alpha I was sigma of W transpose xi, and we have a different W. This would be like WT at the teeth step. The teeth step. Yeah, so actually I should have, to be completely clear, I should have said that these are evaluated using, well, I guess B here. So this is where these, with B evaluated using B and alpha here, evaluated using WT. Because in Newton's method, we use, right here, it's using xt. So here we evaluate the Hessian and the gradient at the point WT. All right, so that's it. You know, I just wanted to sort of explain why it's called this iterative reweighted least squares, and to just sort of show you explicitly what it looks like to when you after you've gotten the Hessian and the gradient, you plug these in and you get this. And I should maybe mention at this point that all of the sort of remarks that I made about issues that can come up with various applications of Newton's method apply here when we talked about Newton's method. Like, you might want to put a step size in here, like an epsilon t for your step size. You might want to, instead of inverting h directly, you might want to solve h. Let's see, I've used x, y, z. What haven't I used? Let's say hu. You might want to solve hu equals g for u, and then use wt minus u to get better numerical stability and more efficiency, depending on, as the case may be. You probably, in general, you want to do this because there are inverting h is not numerically stable. Well, it might not be numerically stable depending on the h. So typically you'll want to use this, actually solve this for h and or for u, and then use wt minus u, and so on and so forth. Yeah, and so I guess the only other comment was that if this is not invertible, if the Hessian is not invertible, then you can always use something like Levenberg-Marquard, where you switch back and forth between gradient descent and Newton's method on the fly. So okay, so that's iterative reweighted least squares for getting an MLE for logistic regression.